Hi guys! I am so excited to be talking to you about this topic today, the reasons for which are manifold. Firstly, it is the topic itself, Einstein's photoelectric effect, which we're finally going to delve into, and also because we have with us Dr. Konstantin, who prefers to go by just Konstantin, who is going to sort of gently guide us through the intricate details of the photoelectric effect. So I cannot wait to get started. This, by the way, is part one of a two-part series, and there is going to be a cliffhanger at the end. So do stay tuned through the entire duration, and I hope the cliffhanger isn't too nerve-wracking that you will be unable to lead a normal life or, not be able to sleep peacefully until the second part comes out. I genuinely hope so. But that being said, there are timestamps in the description below, so feel free to move around the video. And towards the end, by the way, I have a nice little sweet surprise for you. We do talk about physics, but in a slightly unconventional way. Alright then, without further ado, let's get right into it. Okay, thank you so much for doing this, Konstantin. Please tell us a little bit about yourself.
So I started to work here, actually, at the University of Karlsruhe in 2003. Now I'm at Karlsruhe Institute of Technology, which was grounded in 2009. And since the beginning of my activity here in Karlsruhe, I worked in development of superconducting detectors for very broad spectral range, starting from, let's say, standard optical range, so-called single photon detectors, infrared, mid-infrared, terahertz range for development of different types of detectors for different applications, for example, like astronomy, spectroscopy.
So to quickly backtrack a little bit, the infrared range, or the IR range, is part of the electromagnetic spectrum, and it lies in frequencies between 700 nanometers to 1 millimeter. Now the advantage is that because it operates at longer wavelengths, these radiation can pass through clouds of dust and gas in the atmosphere or in outer space with much less scattering and absorption. So they can be used to detect distant stars and galaxies or give additional information than those obtained from the visible light range, as in this picture of the Carina Nebula. For more information, do check out the link to the NASA webpage on IR waves in the description. I've just focused on IR waves, but of course there is the entire spectrum of the electromagnetic waves, which can essentially be exploited to help us better understand the chemical composition, temperature, densities, and a variety of other information pertaining to stars and other astronomical objects, which is basically what astronomical spectroscopy is all about. But I digress. This video is not on that topic. We're here to talk about something else.
So what's a photoelectric effect? There are two types of photoelectric effect. One is external. So when absorbing phone extract the electron out of the photocathode in the real space. And the second one, so-called internal photoelectric effect, when energy of photon transferred to electron which remains in the body of the metal. So now we are talking about external photo effect.
Alright, so before we go in, let's take a look at the experimental setup of the photoelectric effect. We have the cathode, which is the negative electrode. When light strikes the surface of the cathode, it causes an emission of electrons towards the anode, which is the positively charged electrode that takes the electrons, and then these are further detected as photocurrent in the readout electronics. So this is kind of the general setup. Now, of course, this setup can take more complicated forms, such as when we look at the development of detectors, like photomultiplier tubes. And we will touch upon this more in the second part of the video, but essentially the idea is the same. And this ties into the definition of the photoelectric effect, which is basically the generation or the emission of electrons from a surface when it is struck by photons or light. So now we're going to look into the current voltage characteristics of just such a device, after which we will look into the three laws of photoelectric effect that were kind of known in the 19th century, well before Einstein's time, but it is important to discuss these so they thoroughly set the ground for Einstein's discoveries.
So we have current, so we have voltage. And if the photocathode at optimal condition is irradiated by a certain radiation of certain wavelengths, so then with increasing voltage we will,
That's okay.
Another color. So we will build the following current voltage characteristic. It will start from a certain value, then after increasing of the voltage up to a certain value, the current will saturate.
Right.
This is actually the first law of external photoelectric effect. After a certain critical voltage, the current will saturate and will not increase further. So this is in contrast to let's say, for example, Ohm's law.
Right, okay. And the current saturates because all the electrons will have made their way over to the anode.
Exactly.
Yes.
So this, everything can be explained on basis of theory of Albert Einstein.
Right, okay.
So if we will decrease, if we will apply negative voltage, so the current will decrease and at certain value, which is usually called stop voltage.
Alright, so it's voice over time due to some unavoidable issues in the original audio. Essentially, we're talking about the second law of the photoelectric effect. Increasing or decreasing the optical power, in this case, will change the characteristics of our current voltage curve. The stopping voltage does not change if the cathode is radiated by photons of the same wavelength. You can see the difference in saturation current at the low and high optical powers between P1 and P3. So at high optical power of P3, we have higher saturation current.
So this can be explained only by the quantum mechanical theory, and this stop voltage is dependent on energy of the photon.
Okay. So I'm sorry, just to interrupt, for those who might not know what the stopping voltage is, it is essentially the voltage at which no more photocurrent is produced by the electrons.
Exactly.
Right?
So at this stop voltage, the current is zero,
Yeah.
and now no further changes in the state of the system can be recognized if you decrease or increase negative potential further. So this is absolutely zero. But this stop voltage is dependent on energy of the photon, or on valence of the photon.
Okay.
And if now we will consider dependence of the stop voltage on valence, or better to say, let's say energy of the photon, so Planck constant on frequency, so we will come to the following dependence. So it's increases with increasing energy applied photon, but if we will extrapolate this dependence to axis of energy, so we'll come to zero stop voltage at non-zero energy of the photon. So there is some threshold value of the energy of the photon below which the external photoelectric effect is not observed. So this is the short law of photoelectric effect.
Great. And now the most awaited part. Let us look at Einstein's specific contribution. And since you've all been so patient so far, here's a lovely little meme to just get us going. Alright, that's enough of that. Back to Einstein.
So, in 1905, he published a paper describing external photo effect based on quantum mechanical approach. Yeah.
This is a paper for which he eventually went on to win the Nobel Prize in 1921.
Exactly. So, for these publications, for this discovery and explanation of external photoelectric effect, he got a Nobel Prize. So, why it was so important at that time? Because in the beginning, end of 19th century, beginning of 20th century, so there were just two problems which was assumed like the last problem in the physics, which should be solved, and then the building of the physics will be finished completely. This is distribution of an energy spectrum of black body emission and external photoelectric effect. At that time, so it was time born of quantum mechanical physics, and only on base of this approach is possible to explain these phenomena. So what has been written by Albert Einstein? He proposed that energy of the photon, which is observed or irradiated for the photocathode, is divided in two parts. The first part is so-called work function. So this is the minimal energy which is required to be transferred to electron so that he will be able to escape from the photocathode. So let's name it A. And the last part, if energy of the photon is larger, so then electron can be emitted from the surface of the photocathode with a certain energy, kinetic energy. And the maximal kinetic energy of the electron can be obtained out of this equation. So if we know energy of the photon, we can subtract work function, and then we obtain this maximal kinetic energy. So actually, this kinetic energy is not the maximal always. It can vary from 0 to this maximal value. And this variation is dependent on different parameters and different conditions of this external photoelectric effect. So to get explanation, so in this situation, in principle, out of this equation, we will come to, they say, this dependence of the stop voltage and the fixed value of the stop voltage at the fixed energy of electron. So if this energy is fixed, so then by applying of decelerating voltage, we simply break electrons, we reduce the velocity, and at certain energy applied voltage, which is equal to the maximum kinetic energy of electron, we will come to zero state. So that electron will just escape from the surface, having energy equal to the work function, will not be able to reach the end. Because his kinetic energy is compensated by applied electrical voltage.
Okay.
So this already can be explained. So the next approach,
So before we go ahead, so the work function is a property of the material.
Exactly.
Okay.
So that the property of material depends on what quality of the surface, it depends whether we use metal or we use semiconductor or we use other materials. In principle, all matter can emit electrons after radiation. The question is how much energy of the photon we have to have so that the electron will be extracted. Yeah?
Okay.
So
now let's consider something called the three-step model. The three-step model was proposed in 1958 to better explain the process of photoemission of electrons. Essentially, it takes into account the spread of the electron energy in the process of excitation of the electron after it absorbs the photon, then its transport, and then finally its escape from the photocathode. Okay, on to the expert.
First of all, so if we have surface of our photocathode, so then our photon, which irradiates the surface of this photocathode, should be absorbed. Absorption means photon should transfer its energy to electron. The question is, how deep this electron will be excited. Photon can be absorbed very close to the surface of the cathode or somewhere deeper.
Deeper, okay.
So then, after this phenomena, so after absorption, which is once again not deterministic but probabilistic phenomena, because the photon can be reflected or can propagate through without absorption. So the next step, so this electron, before it will escape from the surface and will be actually the photoelectron, this electron should reach the surface. And this movement is diffusive movement.
Okay.
So during this movement, electrons scatter with other electrons and can lose part of his energy. Electron can scatter with the lattice, crystalline lattice, so emit phonons and once again lost part of his energy. The question, how many energy will remain or will survive this electron when he will reach the surface.
So just to quickly add, we're talking about the surface of the cathode, and we're talking about the emission of the electron so that it can then be detected at the anode, where it then further produces the photocurrent. And secondly, when you talk about phonons, phonons are simply quasi-particles which are associated with heat production. Is that right? Or sound, is that right?
Exactly.
That's sound, yeah.
So actually phonons are, let's say, quantum mechanical description of oscillation of crystalline lattice. So if electron or photon is quantum mechanical description of electromagnetic waves, phonons are quasi-quantum mechanical description of waves generated in the crystalline lattice.
Okay.
So here by heat or by energy transferred from electron to the photon, this is absolutely indifferent. So any type of energy can be transferred to the phonons.
Okay.
So and then, some parts of energy of electron in the vicinity to the surface is smaller. cannot be larger than energy of the photon, but can be definitely smaller than. And then this electron should escape. And this escape probability is actually described by this walk function. So if energy of electron near the surface of the photocathode is already below this walk function, so the electron will not escape and will not participate in the current. Independently how large voltage we will apply. When electron come out of the surface becomes positively charged.
Yeah.
And the electron can come back and absorb by the surface.
Okay.
So we need in this situation to apply certain power to electrons with certain force to move it out of the cathode so that this electron will reach the end.
So all the dependencies we've looked at so far can be explained on the basis of Einstein's quantum mechanical approach. However, there are a couple of exceptions that stand out.
But dependence is absolutely opposite.
Yeah, and why? Why would that be?
So
this is something we look into in the next video. Until then, okay, so I just randomly spotted this painting on the wall, and Konstantin is going to tell us what this is. One of them is Salvador Dali, the famous painter, and the other is Pablo Picasso.
Exactly.
Take it away.
Actually, why is this picture here on the wall? So just to demonstrate how theoretical models can describe the real object.
Okay.
So the models are always limited, so they are not able to describe the object, real object in all details. They can describe some part of this real phenomena or object or whatever, but they will miss another one. So, like it's here, you can see, for example, in case of the real, you can see in case of what can be done out of I, but at the same time, this is not the volume like contrast. So in case of Picasso, the volume is here, but well, the shape is not well explained.
So, but the point of the painting is not to say that one is better than the other, it's just to say that there are different approaches.
Different approaches, different point of view.
Okay, thank you. Huge thank you to Konstantin for his time and his invaluable insights. And to you guys as well, if you followed up until this point, it's pretty darn impressive. So stay tuned, hang around. Like I said, we have a part 2 coming up and lots of exciting things to follow. So yeah, I'll see you around. Bye-bye.